Tonight, we're going to talk about a storm. Not a storm on Earth, not a hurricane or a typhoon, or anything that fits inside a weather map. A storm 3 times wider than our entire planet. A storm with wind speeds of 400 miles per hour that has been raging continuously for at least 350 years. A storm so large, so permanent, so defining that for centuries it has been the first thing anyone points to when they show you a picture of Jupiter. The Great Red Spot, the most iconic feature in the solar system, the storm that outlasted empires, revolutions, the birth of modern science, 2 world wars, the space age, and every human life that has ever been lived. And it is dying. Not slowly, over geological timescales. Not in some distant future that has no bearing on anyone alive today. Within 19 years, scientists now estimate the Great Red Spot could be gone entirely. The most recognizable storm in the history of planetary science dissolved. Jupiter without its spot. But here is the part that nobody talks about. As it shrinks, it is growing taller, more intense, more powerful at its core than it has ever been. The dying storm is somehow simultaneously becoming stronger. And understanding why, understanding what is actually happening inside that shrinking red oval, might be the most important thing we have ever learned about how planets work. Before we talk about what is happening to the Great Red Spot, we need to understand what it actually is. Well, because most people have a picture of it in their heads. A red oval on a striped planet, without any real sense of the scale or the strangeness of what they are looking at. Jupiter is not a planet in the way Earth is a planet. Earth has a thin atmosphere sitting on top of a solid rocky surface. Jupiter has no solid surface at all. It is a ball of gas and liquid, mostly hydrogen and helium, compressed by its own gravity to the point where the distinction between gas and liquid becomes meaningless. When we talk about Jupiter's atmosphere, we are talking about a layer that extends thousands of miles deep, transitioning from thin gas at the top through increasingly dense and hot layers until the pressure is so immense that hydrogen itself becomes a liquid metal conducting electricity. The Great Red Spot sits in that atmosphere. It is a high-pressure anticyclone, a system where gas spirals upward in a rotating column, driven by the temperature and pressure differences between Jupiter's equatorial and mid-latitude regions. It sits at approximately 22 degrees south latitude, locked in place between 2 of Jupiter's jet streams, one moving east and one moving west, and those jet streams essentially trap it in position. It cannot move north or south. It is pinned, and within that pinned position, it spins. Anti-clockwise, completing one full rotation approximately every 6 days. The winds at its outer edges reach 400 miles per hour. For context, the most powerful hurricane ever recorded on Earth had sustained winds of around 200 miles per hour. The Great Red Spot at its edges is twice that, and at its peak size, it was wider than 3 Earths placed side by side. The first person to draw what is almost certainly the Great Red Spot was Giovanni Domenico Cassini, an Italian-French astronomer, in 1665. He called it the permanent spot. He watched it for several years, tracked its rotation around Jupiter, and then it faded from his observations. Whether the storm dissipated and reformed, or simply faded in color to the point where the telescopes of the 17th century could no longer track it reliably, we do not know. It disappears from the historical record for about a century, then reappears in the late 18th century, and has been observed continuously ever since. That continuity, from the late 1700s to today, gives us roughly 230 years of documented, unbroken observation. And what those observations tell us is that for most of that time, the Great Red Spot was enormous. early 19th century estimates put it at 40,000 kilometers across, more than 3 times the diameter of Earth. It was so large that amateur astronomers with modest telescopes could see it clearly on clear nights. It was a fixture, a permanent feature of the solar system, as reliable as the rings of Saturn or the phases of the Moon. Then, in 1979, something changed. Or rather, something was finally measured properly for the first time. The Voyager 1 and Voyager 2 spacecraft flew past Jupiter in 1979, giving us our first close-up measurements of the Great Red Spot. What they found was a storm approximately 25,000 kilometers across, about 2 Earth diameters. Smaller than the 19th century estimates, but still vast by any standard. Voyager's cameras also revealed the internal structure of the storm in extraordinary detail for the first time. The swirling cloud bands, the complex internal circulation, the way smaller storms were being pulled into and absorbed by the larger one. For the next decade and a half, nobody was particularly alarmed. The Great Red Spot was large, it was stable, it was doing what it had always done. Then, the measurements started to change. By 1995, the Great Red Spot had shrunk to approximately 20,000 kilometers across. Still enormous, still clearly visible, but smaller. By 2009, it was down to around 18,000 kilometers. By 2012, it had passed below 15,000, less than 2 Earth diameters for the first time in recorded history. Scientists who had been watching it for decades were alarmed enough to publish papers. The rate of shrinkage was accelerating. Something was happening. The shape was changing too. For most of its recorded history, the Great Red Spot was an oval, wider than it was tall, elongated east to west along Jupiter's atmospheric bands. As it shrank, it began to round out. The eastern and western edges were contracting faster than the northern and southern ones. By 2020, it was almost circular. A feature that had been a stretched oval for 200 years was becoming a tight, compact circle, and the color was shifting. The deep brick red that gave it its name, that rich, dark, reddish-brown that made it unmistakable even in amateur telescope images, was fading in patches, becoming more orange, more salmon, less uniformly red. By 2026, current measurements put the Great Red Spot at approximately 13,000 kilometers across, barely larger than Earth, the smallest it has ever been in recorded history. Still visible, still a storm, but a shadow of what it was even 50 years ago, and the rate of shrinkage, rather than slowing, has held steady at roughly 900 kilometers per year. Do the maths. 19 years. Now here is where this stops being just a story about something getting smaller and becomes genuinely strange. While the Great Red Spot has been shrinking horizontally, losing width and length, it has been growing in the opposite direction, vertically, deeper. The Juno spacecraft, which entered Jupiter's orbit in 2016 and has been making close passes of the planet ever since, carries instruments capable of measuring the depth of atmospheric features using microwave radiation. In 2021, Juno's data revealed something unexpected. The Great Red Spot does not just sit on Jupiter's visible cloud layer. It extends downward into the atmosphere approximately 350 kilometers. 350 kilometers deep. For comparison, the distance from the ground to the International Space Station is around 400 kilometers. The Great Red Spot is nearly as deep as that entire distance, and as the storm has shrunk in width, that depth has increased. The storm is not dissipating, it is concentrating. The same amount of energy, the same rotating column of atmosphere, The eye is being compressed into a smaller and smaller horizontal footprint while extending further and further downward. Think about what happens when a figure skater pulls their arms in during a spin. Their rotational speed increases because angular momentum is conserved. The same total momentum is now concentrated in a tighter rotation. The Great Red Spot is doing something similar. As its horizontal extent decreases, its rotational energy is concentrating. The wind speeds at its core are increasing. The pressure differential driving the storm is intensifying. The Great Red Spot is shrinking. And as it shrinks, it is becoming the most powerful version of itself it has ever been. A smaller, tighter, faster, deeper, more intense storm. Dying and strengthening simultaneously. These two things are happening at the same time, and they are both true. So why is it shrinking? This is the question that has occupied planetary scientists for the past decade, and there is, at the moment, no single agreed answer. There are three competing theories, and the honest position is that all three may be contributing simultaneously. The first theory is starvation. The Great Red Spot, like any long-lived storm system, needs to feed. On Earth, hurricanes feed on warm ocean water. When they move over cold water or land, they lose their energy source and weaken. The Great Red Spot feeds on smaller vortices, the little storms and eddies that form in Jupiter's atmosphere and drift into its path. When these smaller storms are absorbed by the Great Red Spot, they add energy and angular momentum, replenishing what the storm loses to its surrounding environment. For most of its history, this feeding process was robust. Jupiter's atmosphere was generating plenty of small vortices to sustain it. In recent decades, that supply may have diminished. The reasons are unclear, possibly related to changes in Jupiter's global atmospheric circulation, possibly to changes in the temperature differences between Jupiter's atmospheric bands that drive the formation of smaller vortices. But if the storm is receiving less energy from mergers than it is losing to its environment, it will shrink. Slowly, steadily, and with accelerating pace as it gets smaller and the ratio of surface area to volume shifts against it. The second theory focuses on the jet streams. The Great Red Spot is trapped between two of Jupiter's most powerful atmospheric jets, one moving east and one moving west. These jets effectively contain it. They are part of why it has stayed in roughly the same latitude for centuries. But jet streams are not static. They shift in speed and position over time. If the jets that bracket the Great Red Spot have been closing in, moving slightly closer to each other and squeezing the storm from north and south, that mechanical compression could be responsible for the shrinkage. The storm is not losing energy so much as it is being physically compressed by the atmospheric structures around it. The third theory is the most hopeful, and in some ways, the most interesting. It suggests that what we are watching is not death, but a phase transition. Jupiter's atmosphere has hosted other large, long-lived storms before the Great Red Spot. Or at least, there is evidence that it has. In 2006, two astronomers observed a smaller reddish storm that had been developing for several years reach a size large enough to be called the Red Spot Junior, or Oval BA. In 2008, that smaller storm passed very close to the Great Red Spot, and the two interacted gravitationally. For a time, there were two red spots on Jupiter. Then, Oval BA faded. Some scientists argue that the Great Red Spot has likely gone through cycles of shrinkage and intensification before in its history, possibly multiple times over its centuries of existence, and that what we are watching is one of those cycles reaching its minimum point before the storm stabilizes or regenerates. Under this theory, the Great Red Spot does not dissolve entirely. It shrinks to a compact, intense remnant, perhaps the size of Earth or smaller, and then either slowly expands again as conditions change or persists as a smaller permanent feature. What does Jupiter look like without the Great Red Spot? It is a question that has never had a practical answer before. For as long as humans have been studying Jupiter seriously, the storm has been there. Every model of Jupiter's atmosphere, every simulation of its circulation, every textbook illustration has included it as a given. It is as fundamental to our mental picture of Jupiter as the rings are to Saturn. But the atmosphere will not be empty where the storm was. Something will fill that space. The question is, what? The most likely outcome, based on current modeling, is that the region where the Great Red Spot currently sits will become a zone of increased atmospheric activity. The jet streams that currently contain the storm will continue to interact. Smaller vortices will form and dissipate. There may be a period of relative chaos as the atmospheric dynamics that were organized around the Great Red Spot reorganize themselves into a new pattern. And eventually, possibly within decades, possibly within centuries, a new large storm may form. Jupiter's atmosphere has the energy and the dynamics to produce long-lived vortices. The conditions that created the Great Red Spot still exist. Whether that new storm will be as large, as long-lived, or as visually distinctive as the one being lost is impossible to predict. Jupiter without a red spot is not a planet we have ever observed. We are about to be the first to see it. Here is what I keep coming back to. Giovanni Cassini drew that storm in 1665. He watched it rotate around Jupiter through a telescope in Bologna and made careful notes about its position and motion. He had no way of knowing he was looking at something that would still be there 360 years later, observed by spacecraft traveling at tens of thousands of miles per hour, analyzed by instruments that can measure atmospheric depth using microwave radiation. Every generation since then has grown up with the Great Red Spot as a permanent fixture of the solar system. It was there when Newton was alive. It was there through the French Revolution. It was there when the first photographs of Jupiter were taken. It was there when Voyager flew past. It was there when Juno arrived. It has been a constant in a universe full of change. And now we are the generation watching it end. Not in a textbook, not in a historical record. In real time, year by year, the measurements get updated. Year by year, the spot is a little smaller, a little more circular, a little more orange than the brick red it used to be. We can watch it through a backyard telescope on a clear night and know that what we are seeing is something in the process of disappearing from the solar system within our lifetimes. There is something worth sitting with in that. We are not watching a star explode or a galaxy collide. Events so vast and so fast, they happen beyond human perception. We are watching something change at a pace we can actually follow. A storm that outlasted every human civilization that has ever existed is ending on a timescale we can measure in decades, in years. The Great Red Spot is shrinking. It is growing taller as it shrinks, concentrating its power into a tighter and tighter core, becoming in its final years something more intense than it has ever been. And within the lifetimes of most people watching this, it will either be gone entirely or transformed into something so different from what we have known that it might as well be a different feature of a different planet. We are the privileged generation, the ones who get to see the end of something ancient. Not as a loss, but as a front row seat to the solar system doing what it has always done, changing, evolving, moving on, indifferent to the fact that we happen to be here to watch. Good night.